So last time we were talking about Renormalons, and we're going to continue to do that today. So we said that typically in quantum field theory you have perturbation series, but actually they're asymptotic. And the kind of growth that you might expect is some power. I think I used two different conventions for this power, whether it's plus n or minus n, but that's just a goes to 1 over a. And there's this factorial growth. So we said we could characterize those series by thinking about doing something called a Borel transform, and that makes them more convergent, because basically we take the coefficients and we divide the coefficients by an n factorial, so we get a more convergent series, and it may be that this thing exists, or it may be that this thing exists and has poles. And if it has poles, as I've indicated here on the real axis, then the inverse transform might not exist. So even though this thing is something that you can define, you can't get back to f. And if that's the case, you can characterize how the original series was diverging based on those poles, and those poles are called Renormalons. So if we could calculate to all orders in perturbation theory and some quantum field theory, like a gauge theory, then we could just calculate these f's. We would find that actually there is this factorial growth, and we'd be able to do this. But we can't do that because we don't know how to do all the diagrams. So in order to give you an explicit example of what we talked about last time, instead of looking at all the diagrams, we pick a particular subset that we can identify, and that's what we're going to do today. We start by doing today. Part of our discussion of motivating why one might want to think about Renormalons was thinking about the pole mass versus the MS bar mass, and showing you that phenomenology starts to work better in terms of the MS bar mass, and then we even went further than that and said we should talk about this thing called the 1s mass, and we'll come back to that discussion today. But I'd like to consider just the explicit calculation of the pole versus the MS bar mass and show you that you can see this Renormalon. So if we want to think about the definition of these masses, then we have to implement those definitions order by order in perturbation theory. And order by order in perturbation theory, we could calculate the f's, but we need to know something about the entire series, and that is too hard to get the complete series. So we'll pick out an infinite subset of that complete series so that we could identify which is unique. And of course, we should pick out an infinite subset that's the easiest to calculate. And the one that we can pick out that's easy to calculate is the following. We look at so-called bubble sum. So graphs with a bubble, and then more and more of them. Okay, so the reason that these graphs are unique is because if you look at any order in perturbation theory, they're the graphs with the most factors of the number of fermions running around in these bubbles. So if you call the number of fermions running around in these bubbles NF, this graph has the most powers of NF. So at each order in perturbation theory, it's unique. It's a unique contribution, and it's pretty easy to calculate because there's only one type of diagram contributing.
What does unique mean? Gauge variant?
Unique means that there's no other diagram. So you might think at each order in perturbation theory there's lots and lots of diagrams. There's only this diagram that contributes to the highest power of NF. It's also gauge invariant, but it's really a unique diagram that contributes to that color/flavor structure. Okay, so obviously an ingredient in this is the bubble itself. So if we go back to the bubble plus its counter term, and we say there's a momentum p going through it, diagonal in color, transverse in momentum, has a factor of NS, NF, some other numerical factors. There's a logarithm. There's a constant. And then there's some divergence, but we canceled the divergence with a counter term, so the graph would look like that. And I'm going to absorb all these things into a single logarithm just for convenience. So I define a constant c bar, which is this 5/3, and then I just put it into the logarithm. OK, so then this is a geometric series, so it's easy to deal with. So g mu nu, which is as a function of p and alpha s, which sums up this chain plus counterterm diagrams, where there's n bubbles here, and we start at the beginning. We start with no bubbles. This thing is a projector. OK, so this explicitly writing out the sum. And what I've done here is I've used the fact that even though I wrote up NF up there, I can convert it to beta naught. So beta naught was 11/3 CA minus 2/3 NF. I can solve that equation for NF and substitute it back in. And that is a convenient thing to do, just because you can think that these terms are then related to the beta naught, which has to do with the running coupling. In some sense, what we're doing is we're saying that even though we're just calculating these NF contributions, we know there's going to be some non-abelian contribution that comes along with it that makes this really into a beta naught. Or another way of saying it is that if you think about characterizing color structures, you could write NF CA, NF squared, or you could write beta naught CA, beta naught squared. And these are equivalent ways of representing the different kinds of color structures that can come in at higher order. And we're just choosing to do it this way with the beta naughts rather than the NFs. So we convert our NF to a beta naught. And it's still a unique subset of the entire set of terms. The terms we're not including are terms like this, NFCA or CA squared. And we're just keeping these guys, which is equivalent to this guy. Does that make sense? Everybody happy? Sorry?
Where are the photon propagators?
The photon propagators. So the photon propagators all cancel each other out. So you get a p squared and then a 1 over p squared, 1 over p squared. So the whole thing looks like a photon propagator just with a bunch of logs. Any other questions? All right. So this is already of the structure where we could think about doing the Borel transform, because we have a series in alpha s, and what the Borel transform meant was taking that series and converting it to a series in the Borel variable, just dividing by n factorial and then doing a sum. So previously, the way I wrote that, for the conjugate variables, we wrote that we had alpha to the n plus 1. And if you think about what we do, we just went to b to the n over n factorial. OK, so basically to convert from this guy to this guy, that's what we did. And we had to take special care of the first term. But other than the first term, we just had this replacement rule. Now, it's a little convenient actually not to do that with exactly the same variable, but a slightly different variable that's just rescaled. So I'm going to use a slightly different variable here, which is typical. So what we'll do is we'll say that instead of just taking along the alpha s, we'll take along with it the beta naught. And we'll say that the conjugate variable to that is u instead of b, but it's just a rescaled. We're just taking something along with the coupling constant, which is we're always free to do, is just a multiplicative factor. Now, if we look at this diagram here, the factors of the coupling that we've included are all the ones that are attached to the bubbles, but there's two more. There's one here and one there. And if we're going to make this replacement rule, we have to identify all the factors of alpha s, because they're all going to disappear and become u's. So we have to take these guys into account too. So we have an extra g squared. Which I'm going to write in terms of this variable. Okay, so there's an extra factor of g squared from the ends. And if you think about what that means, it means that every diagram that we're considering here starts with n equals 1, so we don't have to worry about this delta function term. Starts with n equals 0. There's no term with no couplings here. So then it is literally what I said, that we just take this factor and replace it by that factor. Okay? So a Borel transform, remember, is a transform of the variable alpha s. Alpha s goes over to a different space. So it's not a kinematic variable. It's not like what we're used to transforming in, but it's perfectly fine. For those people that came in after I said this, there's no lecture on Thursday. So let me use the following notation, taking that g squared along with our geometric sum, and now expressing that whole thing as a function of momentum still and u instead of alpha s. So I replace the alpha s's. And I get that series, which we can see is just an exponential series. So I can just calculate the sum. Borel variable u log which, if you have an exponential of a log, is just a power. So let's organize it that way. let me write it this way. So just writing the exponential log as that thing raised to the power u, taking the mu squared e to the c bar u, just that's a constant. And then taking all the factors of p squared, there was one from here, and then there's u of them from there, but I took an extra one from here, and multiplied on top and bottom by an extra p squared. Hopefully I got the sign right. Looks like it should be plus, but. Okay, so this thing is kind of nice for computations because when you stick it back into our bubble sum, when you stick it back into the diagram, this bubble sum back into the diagram we want to compute, we just have effectively a modified gluon propagator. So think of it as some kind of modified gluon propagator. Maybe I should write it in a different color. So it's just like this, where we use a different Feynman rule for that propagator. Okay, so it's not actually that. Doing these types of bubble sum calculations is not any more hard than doing a one-loop calculation. You just have to use a different power for the propagator. But your Feynman rule tricks can. Your Feynman integral tricks can handle that very easily. Okay, so it's about as hard as computing this one-loop graph. So let's call this thing sigma bubble. And let's think about calculating it in terms of the MS bar mass. And then we also cancel any 1 over epsilon poles, which we're not really interested in here. The 1 over epsilon poles actually come from, if we think about what happened with the variables, they come from the case u equals 0, which is the log divergent piece. And if you think about what we want to do in order to look for poles, so u equals 0 is actually related to the ultraviolet divergence. While values u greater than 0 and u less than 0, those are probing these poles that are off the axis in the Borel plane. And it's those power law divergences that are probing for Renormalons. And we'll see that they lead to poles in the Borel plane through this modified propagator. So let's calculate the goal here is going to be to calculate an expression that relates the MS bar mass and the pole mass. And that'll be an infinite series, and it will be a function in Borel space. Alpha S space, that would be an infinite series in alpha S, because we've included an infinite number of alpha S's in our diagrams. And we go over to Borel space, there'll be some functional relation between those two masses. Okay, so what's the definition of the pole mass? If you go back to the propagator and you write it in terms of the MS bar mass, so you formulated your whole quantum field theory in terms of the MS bar mass, you calculated that bubble sum, called it sigma, wrote it in terms of the MS bar mass. The general structure of sigma would be that there's some constant piece, which I'll call sigma 1. And then there's some sigma 2 piece. And the pole mass is where, the place where you demand that you just have p slash minus m pole. So another way of saying that is that if p squared is equal to m pole squared, you just set that to be 0. Which I can write as an equation like that, and then I can square it. So m pole squared, which is p slash squared, is m bar squared, this thing squared. And if you just think about what that gives, this is giving some equation that looks like m pole is m bar, and then 1 plus sigma 1 plus the extra stuff. So let's do that and figure out what we get from this diagram for the sigma. So it's the usual one-loop type calculation. Except instead of the gluon propagator, I have this g mu nu thing. Which at this point is in alpha S space, let's say. And then I have the fermion propagator. And I've taken into account all the g squareds and the alpha s's in here. And so to go to the Borel space, I can do that under the integrand. So I just take g squared g mu nu bubble, k in alpha s, k being the loop momenta, and just send that over to this thing that I'm calling g squared g mu nu bubble, which is not a function of g squared anymore, but just a function of k and u. And as long as you're staying away from u equals 0, there's no issues related to the order of doing those operations. So at u equals 0, you have to be actually careful if you really want to go figure out what's happening at u equals 0, but that's actually not what we're interested in, so we'll just ignore what's happening at u equals 0. Okay, so combine, stick in the expression that we had over here for this guy, and it's just some p squared to a power, so it becomes a k squared to a power. So you have k squared to a power, you have this guy to a power, use the usual tricks, combine denominators. Do algebra. And you get some expression for sigma 1 in Borel space. And then from that, you can construct the relation between the pole mass and the MS bar mass. And it might not surprise you, having done some one-loop calculations, that you're getting some gamma functions. So after the dust settles, this is what it looks like. Six, 1 minus u, gamma of u, gamma of 1 minus 2u over gamma of 3 minus u. So the piece that we just calculated, or sketched how you would calculate, is this. And then there's the tree level relation between these two things, which in alpha S space was just that m pole is equal to m bar. But when you transform 1 to the Borel space, you get a delta function. So this comes from just that equality at lowest order. It becomes a delta function in the Borel space. So now if you look at this and you ignore u equals 0, then the closest pole to u equals 0 is u equals a half, coming from this gamma function. And remember that we had a kind of notation for the strength of a Renormalon. Those closest to the pole, closest to the origin, were the strongest. So the strongest Renormalon here is a u equals a half Renormalon. That strength was related to the fact that basically you got something of what would be, in this case, 2 to the n factorial. So 1/2 to the minus n. And so the guy that's closest gives the strongest prefactor to the n factorial growth. That's where that naming came from. Yeah.
So there weren't any poles in, the only pole in the modified Coulomb propagator was it, well, like the one that made the
Yeah.
denominator vanish, but the rest of the poles came from actually doing the one-loop diagram. Wasn't
That's
actually
right.
inherent in the series.
Yeah, so what you're doing is, so you're actually thinking of probing the infrared structure in this loop. That's what the gluon is doing. And the modified propagator p squared to the u is just giving you a kind of a regulator, if you like, which is the u, that's allowing you to probe what's the infrared structure in powers in this loop diagram, not just kind of logarithmic divergences, which we usually focus on, but also in power law sensitivity to the infrared. So it's like probing low momentum gluons with this modified gluon propagator. And that's what's resulting in these poles. You're probing the infrared structure of the loop. So there would be some other terms that I haven't written. So let me just comment that there's actually a term that's proportional to 1 over u that would make it finite at u equals 0 if we're more careful and we carry out the renormalization properly. And I also wasn't so worried about anything analytic in u, so I only was looking at these gamma functions. Okay, so if we actually just specify ourselves so that u equals a half, we can simplify things even further. So I'll stick in u equals a half. And if I stick in u equals a half, this becomes mu over m bar e to the c bar over 2. I just put this 1/2 in there. All this stuff with the gamma functions becomes a minus 2 over u minus a half. So there's a pole. It's sitting on the real axis, and we can't do the transform.
At this point, can you drop the delta u?
Um,
Because you know it's not.
Yeah, I don't really need it. But just sort of for completeness, I kept it. Yeah. If I just wanted to think about this term, I could drop it. Yeah. So let's think about the inverse Borel. So we wanted to do an integral which in this U space would look like this. So U is the conjugate variable to 4 pi over beta naught alpha s of mu. That was what we transformed. So that's the difference between our old notation and our new one. We just have a conjugate variable to this thing. And so this has an ambiguity because on the real axis, we have a pole at u equals a half. So there's that pole at a half. And you have to decide, do we want to go around that above or below? So I mentioned this last time. We could think about going past the pole that way or going past the pole this way. And the fact that we have to make a choice means there's an ambiguity. And if you like, you can say, well, let's average above and below, but the ambiguity would then be something like a half going around the pole. So let's actually look at what the ambiguity is. So the ambiguity, well, if we go around the pole, we get a 2 pi I. There's a half. Integral around the pole. This factor. So mu, c bar over 2. R. And if we put everything together, the rest of the prefactor, there's a CF over 3 pi beta naught. And there's also another M bar, which is this M bar that's out front. And I combined the -2 with the 6 to get a 3. So the M bars actually are canceling. Close on the pole, stick that value in everywhere else. We get that. Does anybody recognize this?
It's like an instant.
It's lambda QCD, yeah. Yeah, it looks kind of like an instanton with the exponential, but this particular thing is actually exactly lambda QCD. So if we solve this and we invert it and we solve for alpha s, that would be the usual formula for lambda QCD, alpha in terms of lambda QCD. So we've just shown that the ambiguity up to some constant prefactor is exactly lambda QCD, and that is exactly our physical idea that we said last time, that the pole mass has a delta M of order lambda QCD ambiguity. And we've just seen that explicitly arise from calculations with this Borel space. Okay, so that's kind of neat. Yep.
Is there a way to be careful about the I epsilon prescription when you do these Borel transforms?
Yep.
Because it seems like you just multiplied a bunch of squared plus I epsilons together and then just ignore the I epsilon?
Yeah, I didn't actually ignore the I epsilon. The reason I wrote it as minus p squared to the power was because of that I epsilon. I didn't write the I epsilons on the board, but if I had, it wouldn't change anything that I wrote. So one way I can say it is that when I actually did these loop calculations, I was actually careful about the I epsilon.
Yeah, I'm not worried about like getting the sign right,
Yeah.
like of logs. I'm worried about like actually defining products of distributions right, and then like when you interchange the order of integration, presumably
Yeah.
you're doing something violent.
You mean the order of the summation and the integration?
Right.
Yeah. When you interchange that order, the only thing that so you can do it the other order, the only thing that actually goes wrong, and it's much easier to present it in this order, this is why I did. If you do it in the other order, the only thing that will change is what happens at u equals 0. So you'll actually see everything that we saw, except that u equals 0, it'll be slightly different. And that 1 over u term that I was talking about, if you want to get that right, you have to think about the issue of changing the order of integration more carefully than I did.
Okay, but near u equals a half.
But near equal u equals a half, it's exactly, this is the right result, and near any other u except u equals 0, we're okay. Yeah.
So which counter do we pick?
Sorry?
Which counter do we pick to define?
We don't know. So the ambiguity, you have to make a choice, right? If you make this choice, you've picked one definition. If you make this choice, you've picked another. And I said we can quantify the ambiguity in our choice by thinking about it as half going around the pole. That's kind of a measure of the ambiguity that we have in which way to close. It's an ambiguity.
I know, but we get to define how we calculate, right? So when we say M pole,
Yeah.
what do we mean by?
Different people mean different things. I mean, you're not going to see this, right, unless you go to all orders in perturbation theory. So order by order in perturbation theory, you will never see this pole. So unless you're working to all orders, as soon as you work to all orders, you have to make a choice because of what we just did. If you work order by order, there's no choice to make, and you just order by order define it with the usual definition. So the moral is not how do we define M-pole. The moral is we should use something else other than M-pole because M-pole has an ambiguity.